So the concept for this session arose out of a working group in the LTR network that myself and Corinna and Renee contributed to. And that working group was an effort to develop best practices for publishing modern ecological and environmental data sets that are becoming increasingly large and complex. And so these data sets require more than a collection of simple data tables that can be held in one data repository. And so as data managers in the ecological sciences, we thought of these as special case data sets. And as we encountered them with more regularity, we realized that we didn't really have very many templates or guidelines on how to publish them with the metadata needed to find and reuse them. So for example, what's the best way to publish a modeling study where model parameters, input variables, and model executables, as well as output files, are all required for reproducibility? And in a microbial ecology study, we might publish the nucleotide sequencing data in a specialized repository like NCBI, but the environmental and experimental observations might go into a more general repository like the EDI repository. So what metadata should we provide to make the connection between those two different data sets clear? And how should we approach publishing data from small moving platforms like UAVs or drones? And in those data sets, the metadata describing the platform, payload, flight plan, and image processing can be either not really standardized because they're fairly new data sets, or they're specified only in proprietary software. So this working group got together to develop a best practices guide, which is what Renee is going to present on in our first talk. And our goal was to try to give ecological data managers a template for how to publish these data sets. I'm going to share my screen here real quick. Forgot to do that. Okay. So this session is an attempt to continue this conversation that started in the LTR network and hopefully bring it into a wider community. So today we have assembled several experts in the field of environmental science and data management to discuss the state of the art in publishing some complex data sets. And we're looking for community participation to determine next steps. So the two things we're hoping to accomplish here are, we want to introduce participants to recent developments around publishing, discovering, and reusing modern ecological and environmental data sets. And we want to answer the question, should this community be doing more to develop best practices for publishing modern data sets as they become more complex and varied? So we have 5 talks. We can't cover the state of the art in publishing all kinds of modern data sets. So these talks roughly cluster into 3 themes. First, complex ecological and environmental data sets generally. We also have a section on small moving platform or drone data sets. And we have some presentations on simulation modeling or other computational data sets. So during each talk, you're invited to enter your thoughts and questions into the collaborative document that I linked. We're going to have speakers follow that document and answer questions. So it'll be sort of an asynchronous QA session there. And then at the end of the 5 talks, we're going to send people into breakout groups with our speakers to discuss next steps. So without further ado, I'm going to introduce our first speaker. That's Renee Brown. Again, she's the information manager for the McMurdo Dry Valley's LTR program. Take it away, Renee.
Thanks, Greg. Yeah, so as Greg said, we developed this best practices guide within the LTR network and the Environmental Data Initiative called Data Package Design for Special Cases. And so I'm going to just go quickly as I can through the summary of that document so that you have a sense of the work that we did. And hopefully this will inspire further discussion about where to go next from here. I want to acknowledge my fellow working group members, including Corinna and Greg, who are co-leading this session with me, as well as several others, some of whom are here in the audience today. I also want to acknowledge NSF, who provides funding to the LTR network and to the Environmental Data Initiative. So for those of you who aren't familiar with the LTER network, or the Long-Term Ecological Research Network, it was established in 1980 by NSF to promote long-term scientific investigation of ecological processes, and to also promote comparative research and syntheses across sites and ecosystem types. We now have over 40 years of data collection, and each site, there's approximately 28 sites, I believe right now, have professional data managers. And the LTER information managers were responsible for setting some of the early foundations for managing ecological research data. Part of what came out of that work was the Environmental Data Initiative, which is a data repository established in 2016 for ecological and environmental data. It's a FAIR repository. It's a primary repository for the LTR network, but it also serves many other researchers and research organizations. It uses the ecological metadata language standard for encoding rich machine readable metadata. So I'll be referring to EML throughout my talk, and that's what that refers to. And EDI offers many other services in addition to hosting our long-term data in the LTR network. So we developed, as Greg mentioned, we developed this best practices guide within the LTER and EDI for archiving what we call special case ecological data packages. And to the right, you can see the chapters in our guide. And so these were the sorts of data sets that we focused on, and I'll go through each of these in further detail for the rest of my talk. When we say data packages, we're referring to a published unit of data and metadata together. This is the convention at EDI. A data package may contain multiple entities, such as tables in CSV format, spatial data processing or modeling code, documents, and/or compressed file collections. This guide was created primarily for the LTER information manager community, who use EDI to archive their data sets using the EML standard, but these practices can be easily adapted to other use cases. The general chapter structure provides an intro, considerations, and recommendations, as well as examples of published data packages already in EDI, and as well as additional resources that we knew about at the time that we published this earlier this year. Recommendations come complete with EML code snippets as well to make this process a little bit easier. So I'm gonna quickly go through this section. First two chapters were surrounding code and model-based data sets. We have a couple of speakers that will be talking much more at length about this later, but it's there to refer to. Again, there's several archives out there, including ComsEasNet, which we'll be hearing about more later, the GitHub plus Zenodo connection, which is pretty common, as well as EDI. We focus here on EDI. In the guide, we provide a nice flowchart to help you decide what you want to archive, as this can be a complicated decision depending on what you're trying to archive. But the key recommendations here is that you should include a code meta JSON file to provide code specific metadata in addition to the EML metadata. And for models, we recommend that you include your model parameters. If you are trying to archive very large model input or outputs, we recommend to put those offline, and we have another chapter about that. But really the key here is that we want users or data managers to think more about research transparency rather than exact reproducibility. Our third chapter is focused around still images and documents as data. And so these can include lots of different things. that I've spelled out here. Why would you want to do this? Well, there are a number of reasons. A couple here are to enhance the credibility of associated data, to provide opportunities for new analyses, and to improve ease of access. So, for example, paper, hard documents may be kept in somebody's office, but if they're archived online, then a lot of people can access them. And just an example from the McMurdo Dry Valleys, LTER, where I work, we have these long-term stream gauge records, and you see here that at the beginning of December, we have what we think may be a faulty sensor, but in fact, if we look at our field notes, we can determine that researchers visited the site and the stream was actually not flowing. And that is the case in Antarctica. Our streams only flow for 1 or 2 months out of the year. We can look at another part of this record and associate it with the field notes and get some additional information. It was a beautiful day that day. So maybe not something you would want to put in EML, but definitely something to archive to help improve this data set. So our key recommendations with these types of data are to include what we're calling a data inventory table, which there's an example on the right that serves as a document catalog and provides an additional source of metadata to enable optimal usability. There are lots of other kinds of images that we would like to refer you to other chapters for more detail on those. Another specific use case in our group is data in other repositories and what to do about archiving these data in EDI. Why would we want to do this? Well, to enhance discoverability and preserve data relationships across multiple repositories. Funding requirements may require specific repositories. Meanwhile, EDI is a recommended repository for LTER. So it helps with discoverability. Sometimes it's better to publish data in specialist repositories. This is probably our longest chapter. Here are some common scenarios. I just mentioned this one. Here we would just like to say, you should enhance the metadata, but don't duplicate the data. In fact, we never want to duplicate the data, right? In the second case, the data might be published in a specialized repository, such as NCBI, and then linked to an ancillary or supporting data set that is being published in EDI. So we might have genomic data that is archived in NCBI that we need to associate with biogeochemical data that we archived in EDI. So here we recommend including a data inventory table similar to the example I showed in the last slide. And then our third use case here, or scenario here, is that one or more data sets from other repositories, including EDI, could be used to create a derived data product that need archiving in EDI. And so here we want to, I guess in all cases, we want to always include enhanced metadata using the EML standard, as well as a data inventory table. And key metadata include all the standard things like abstract methods and so on. For spatial data, we recommend GeoTIFF or GeoPackage formats. There are other formats to consider, but they have various limitations. But the bottom line here is to avoid proprietary formats. Recommended elements, these are EML specific, is to describe these data as other entity or spatial raster vector, and then include the appropriate keyword in the metadata so that it's easier to discover and find. And then also consider including GIS software compatible metadata, so that because GIS software cannot ingest EML. And then finally include the format name, and there's some additional information about this in the guide. I'm going to skip quickly through this one because Jane will be talking more about this, but we do have a chapter regarding data from small moving platforms. Key recommendations are to include raw data, key derived data, and processing code. There are lots of various things we recommend for the metadata. The bottom line is there are multiple ways to do this, and I believe Jane will be telling us more about that in her talk. And then finally, our last chapter is just in regard to large data sets. This is specific to EDI. And we recommend that the data are copied to hard drives. They include EML metadata along with the same data inventory table that we've talked about before. And these are what are archived in EDI. EDI keeps those hard drives that are available to data users, and the metadata are fair, and the data are stored offline. And so with that, I'm going to end. I have put some links here with the resources. So the first link goes to the R Bookdown manual. This is the easiest way to get this information. It is also archived in EDI. It's a document, so as a PDF. And then we also have a GitHub repository where we can continue this work. And this presentation is linked on the session website. All of these links are clickable. So I hope you find this resource useful down the road. Thank you.
Thank you, Renee. I'm going to pull up our next presentation, which will be a video. Work. Okay, so our next presentation is going to be from Dr. Carl Bediger. Carl is assistant professor at the Environmental Science Policy and Management Department at UC Berkeley. He's also a co-founder of the R OpenSci project. One of the founders of the Berkeley Institute for Data Science, and a, let me make sure I get this correct, and science advisor to National Center for Ecological Analysis and Synthesis, or NCES. I'm presenting video. Carl is here live and he will be answering questions, and we'll see him in the breakout as well.
Hello, I'm Carl Bediger from UC Berkeley, and I will be talking about advancing metadata formats for modern ecological and environmental data. So rather than go into too many technical details, this brief talk will be a survey of some recent tools that I and others have been developing. How do you build tools ecologists will really use? Well, after a detailed user analysis of many years, we learned an ecologist can figure out to use just about any piece of software, no matter how hard it is, as long as it's in R. So each of the tools we will highlight will often show building an R package that connects with other pieces of software to make these things a little bit more accessible. I will also present most of these examples through the lens of some recent work that we have been doing that's focused on ecological forecasting. I think that many of the challenges we've come across in forecasting are true in other areas as well, as I think you will see. I'll start with this famous figure from this Waterman et al. Paper in a special issue of Science back in 2011 on big data. It was certainly formative in my career and something I've tried to aspire to, where you follow this detailed process of the data acquisition workflow and the analysis workflow, and everything is kind of captured en route and put into a permanent archive like in Data 1, and then you just have sort of the paper here on the end. The trouble with the forecasting workflow is you never really get to that static product. You're just constantly churning through this. So we have the data acquisition workflow. You're constantly getting new data and constantly making new forecasts as you both get that new data and as you update the method. And you never get kind of a static product. And so this creates kind of some additional challenges for tracking the products that are going in and coming out. So let's take a look. So we'll focus right now on forecasting coming from NEON data products. So the NEON National Ecological Observatory Network produces many, many small provisional files. They don't go into Data 1 right away. And they're these individual CSVs that differ by the product in question, the month that they were taken, and that's the site that they were. And this workflow creates some provenance issues. For instance, those individual CSV files, NEON will sometimes rename them. So when you make the API request, you get back a file with a different name, but in fact, it's the same data. And occasionally data errors are found and those data files are corrected, but the original version is now inaccessible to the API. So to deal with these challenges, we built a package neon store. It's very simple process. It requests all of the individual files, downloads them, but it tracks the provenance using a strict hash-based system. So it knows when a file has not changed, and you can avoid data duplication or unnecessary downloads. And it also stores all of the raw data files, so you can go back and get your previous versions while always using the most recent ones. It will also stack all of these small individual files into a relational database called DepDB. So it's a columnar local database. It installs easily as an R package, so no external server required. And it's amazingly fast, and you're no longer limited to the kind of data you can fit in memory, like as you would be in traditional R. So this data structure onto the metadata. We needed a metadata description for the individual forecasts. So there's now a draft standard you can see over here at this DOI, which basically just extends existing ecological metadata language standard to describe a forecast. And so, of course, there's the EML R package for working with that, allowing many users who are not familiar with XML can work directly in R. Under the hood, that package now converts the ecological metadata language representation into this JSON LD format, which is very powerful and flexible, and has allowed several derivatives to be built on top of it. Just to highlight another, this package data spice, for instance, works with both EML and the schema.org data descriptions. It's a very kind of lightweight way for a user to make some basic metadata. You can take in formats as well from simple CSV tables to describe the metadata, or YAML like we do in this helper package Neon Forecast. We also found it very important to track the provenance of all of these steps. So while the forecast file might have its own EML describing what's really inside that forecast, we need to describe the provenance of this whole chain. So we do that in those JSON LB descriptions, which we just represent in the kind of standard prov ontology in DCAT2, or that maps nicely to schema.org. So you can do it into one using one of these structured provenance languages, but being able to interact with that in R is again very powerful. So there's at the low level, the JSON LB R package, and then being able to query RDF, that kind of linked data structure that you're getting from JSON LB in the first place. We didn't realize, well, there's no good tools to do that yet in R. So we built this RDF lib package as a wrapper around the Redlands library. And that's great for relatively small to medium size triple stores. So for instance, for the metadata works really nicely. For something that's more complicated, really, really large triple stores, accessing an external database through Virtuoso is really helpful. So there's this R package that will both take care of installing and launching Virtuoso for the user, and then once again, allow you to make simple Sparkle queries like the one shown here on the right to investigate provenance. And we'll show you in a minute what we can do with that kind of query. So here, this is a graph of the actual provenance compared to kind of idealized picture for a forecast. And you can see that if this was the idealized picture, there'd only be one triangle of each color, meaning each month a new forecast would be released. But you see multiple colors of the red and then of the different greens, because that forecast file is often updated. You can see that any individual marker here corresponds to a different content of that file. So here we have the exact same input data, but two different scripts, two different R scripts. So the actual method was changed, and that caused it to generate this sort of two different versions of that forecast. Most of the other times, the changes have been caused by the input data changing. So the input data was updated before that month came to an end, so probably due to underlying scripts that generated that input data. So we can kind of get what actual provenance looks like versus idealized provenance by being able to do this trace. In the end, you may decide, oh, well, all of these earlier versions weren't necessary, and we just want to preserve for the long term sort of the latest version, but we can do that because we can tease apart the individual pieces here. So the last bit of being able to do that trick was to be able to refer to any individual moving part of a forecast before it appears on a permanent archive with a DOI. As we pointed out, both everything from provisional data coming in to the forecast we are producing in this kind of constant chain is happening a lot every, perhaps daily, perhaps monthly. And so being able to refer to specific versions is very important without having to archive every one of them. Also, being able to do all this in R, being able to do it in a scripted way is equally important. You can't do something like read.csv directly with a DOI identifier. as you know, DOI is resolved to landing pages, and you just get a bunch of HTML that way. What you can do is read.csv and use this package called content ID or contented and resolve like you would resolve a DOI. But instead here, I'm resolving a hash, in particular this SHA-256 hash, which is literally the hash of the content I want. So here again, this is an identifier that's guaranteed to be unique to that data that we're trying to read in. And it has several advantages over using a DOI. So resolve, what that is doing is looking for various places where it can find that exact content. For instance, that file may exist locally in a shared folder and it knows it's exactly the content you want because, well, the SHA-256 hash matches, but it can also find it in various repositories. This is a distributed approach because it works in multiple repositories. For instance, here you'll see this particular data file can be found both in permanent archives like KNB and on more temporary archives like GitHub or the URLs, as well as on the local computer. Great if you find a local copy, you don't even need to download any bytes from the rest of the sources. So being able to do something like resolve hash, this works with local files or draft files where you haven't yet published anything. You can stick something onto a remote URL that's not archival, and you can have that as one of the places it can look. But also many data repositories, we can already query for objects by hash. For instance, data one, we can request, can you find any object that has this matching hash? Using a hash is fast, it's free, it works offline, it works in a decentralized way. So two different researchers working with the exact same data will compute the exact same hash for that file. And these IDs are sticky, they can't get disattached or lost or out of sync in some metadata file, because if you have the data, you know it's hash. And of course, you get cryptographic integrity for free. So again, the content ID package helps you work with these by doing this kind of generate these hashes and resolving them. So I'll end with that. This is, of course, like thank lots of individuals who've been involved in these various projects and a collection of different financial support we've had along the way.
Okay. Thanks to Carl for that presentation. We will see him in the collaborative document and breakout sessions. Our next speaker is Dr. Jane Wingard. Jane is lecturer at the Department of Electrical Engineering at the University of Cape Town, and she's going to speak on data from drones and other similar platforms.
Thanks, Greg. Should I share my screen?
You should be able to go ahead. Yep, here it comes.
Did that work?
Yep, looks good.
Great, thanks. I guess a quick clarification. So this work, well, some of this work began at the University of Notre Dame, where I was based. I've since moved, hence the change. But the work that I've done that I'm presenting on my own was done in collaboration with my co-PI on a project, Dr. Charles Waterman, who is still at the University of Notre Dame. Okay, quick introduction to the nuances of drone data management, a couple exemplars, and then the project that Charles, Chuck, and I have been working on and lessons we have learned. Data coming off drones is complex, and the pipeline from sensor in the air through to published data set has many stages, many possible points of human and machine error, and capturing all that information, which ultimately is actually all necessary, is painful. So actually based on the ESIP drone cluster, Chuck and I put together a proposal that was going to attempt to address this, and I will talk about the outputs of that project towards the end, but I want to talk through some of the key exemplars in the community as well. But in brief, everything from what question am I attempting to address through to where is this data eventually going to be used are all important, because what question am I attempting to answer influences the platform I choose to use, the sensors I put on, how I arrange them. That's obviously all influenced by broader high-level project mission. There is a whole lot of legislative requirements around flying any kind of drone, and that information is important either from a organizational safety and regulation perspective, but also from, if I want to publish this information, I need to prove that I captured it legally as well. I want to broaden my definition of drone, not just to the flying things, but because we and other people in this community have specifically taken the time to attempt to think about, okay, there are many things called a drone. There's the small ones that your teenager is flying, and the slightly bigger ones that your scientists are flying, and then there are very large scale ones that NASA are flying, and there are things that go underground, and there are rovers wandering around agricultural fields. And it is helpful if we, as we build the tooling for that suite of things, if we think about the broader suite. Yeah, so eventually you have your platform, you go and fly, and you get your data, and you do things to it. And all of those stages, there is information that is important. I want to start with the takeaways. I changed this just now because it sounds like this is kind of the key points that this audience would value. From 5+ years of wrestling with the complexity of the drone data capture stack, key outputs are use standard ontologies and make modular ontologies. Ontology development is hard, but the tools for this have really improved significantly. Ontology alignment is time consuming, so joining the ontology that you built for your domain with some of the standards that the previous speaker just mentioned, and I'll talk about as well, such as Prov, DCAT, OWL time, is also time consuming, but it reduces your redevelopment time. Automate metadata capture. Our data pipelines are only getting more complex. Big data might be a slightly dated buzzword, but the more devices we are having access to is just increasing the complexity of our data pipelines. And you need all that information if you want to be able to do robust science on it. And then use the open semantic web technology stack. This isn't a single definitive thing. When we first started, it was not mature enough for what we were attempting to do, but I would argue that it is mature enough. You need an expert in the domain to help you select the particular technologies you want to use, but the advantages having your data in machine readable, machine reasonable formats. So in a structure that machines can make decisions and expose knowledge, not just information and data points from your data set, is well worth the effort to implement the technology stack that's required to do so. Okay, I wanted to point to some examples because the path to tooling for drone data capture certainly hasn't been done by myself alone, and there are key examples that are well worth looking at. Probably the first was Open Topology. This is a portal where you can archive LiDAR captured with captured both drones. They had to define their own metadata and what they considered important because there was nothing when they started doing this these 5 years ago. The Australian, I forget their acronym, but they have a drone cloud project, which is an attempt at a national archive resource that is directly linked in with basically Jupyter Notebook-based drone data processing pipelines. And similarly, they have had to work out how and what metadata is important to capture. The Turn, which is basically their equivalent to LTR project, has done some very fundamental work that we are reusing in terms of thinking about how you talk about, in terms of metadata, a site that a drone flies over. So in LTR or NEON context, they have multiple sites at different locations in the country, which are characterized by just different ecological and topographical factors. And Turn has done some really good work in terms of trying to create terminology that is digitized and ontologically robust that we can use to talk about those things. And that is key when you start flying drones over multiple areas with different underlying topographies and ecologies. The USGS has by far been leading any significant effort to digitize and publish drone data. So all credit to Joe Adams and Ryan Long-Henry there. They have everything from defined vocabulary and standardized directory structure through to internal tooling for their mission planning and safety management. And they are publishing their data sets that are coming off drones. It is not fully semantics enabled, but again, leading the way in terms of starting to create some standards and some best practices. So well worth referencing and building on. Others, LTR was mentioned already, and Neon. Neri, I guess, is the one that hasn't been mentioned. They have a suite of drones that are rapidly deployed and have built a sophisticated pipe, including an app, a phone app that allows you to, while in the field, in a disaster situation, tag where you are flying and automatically have your data streamed to a cloud where it can later be further annotated. I should point out that all of these groups have created these stacks slightly differently because the technology in this space has been changing so quickly, and they've all kind of evolved over the last 5 odd years. And none of us had a standard. Nobody had a reference we'd go to. We've all been making, and I've had the luxury of not having to build something that functions now, because that wasn't at any point in time. My role was never to fly drones for a scientific mission. My role was to develop tooling. But these organizations have had to, out of necessity, their scientists are flying and capturing information, and so they've had to create something. And now we're at this interesting point where all of these groups have developed well worth referencing infrastructure, and the question is how to move it to the next level of full engagement with the semantic web stack. So to that, 2 things that are happening at the federal level. There is a federal UAS, unmanned aircraft systems workshop that I think they're coming up for their 5th version. At the March instance of it this year, a number of speakers were speaking to the semantic technology stacks that they are using, and we are currently attempting to write a white paper with the goal of pointing out to key federal leaders that it would be well worth us having at a federal level a group that created some standards, because then all of the federal organizations who are flying drones would be able to benefit from reusing those standards. So obviously USGS and DOT and even the military are involved in that. That should be coming out in the next month or so.
Jane,
yeah.
Just a quick time check. We're at 9 minutes.
Okay, yeah. There's far too much to say about the story. So my Landers project, which is linked and network drones, was attempting to make steps towards fair drone data capture. We wanted to do those things that I said at the beginning, automate the complex drone data pipeline, so that Tom, Dick, and Harry, who are flying drones for everything from NASA through to small-scale community college, would have robust data management infrastructure that they could deploy locally for 0 cost, and be able to publish data that was robust enough for third-party scientific users to take and trust. Probably 2 key things. We have spent a huge amount of time working to align ourselves and integrate the many robust good ontologies that are already out there. And the technology step we have, after many iterations, landed on is for capture of the information of the system that you are flying, including your mission, your sensor, your drone, your safety, is shackle-based or web forms generated from a shackle shapefile. The shapefiles are defined by our underlying ontology, which is based on all of those other ontologies and some pieces we've added. The drone and on the ground, you are deploying a Sparkle endpoint on top of a RDF triple store. There's a handful of defined RESTful API calls, basically defined queries. And we are providing a linked data platform wrapper such that users can bring their own backend meaning autopilot, sensors, and archive. So the point of using the linked data platform, that allows you to store all your metadata in a graph, and so that makes your data searchable and queryable, but then resources such as imageries or LiDAR captures which are far too big to go into any kind of triple store, are stored in whatever resource you like. Our demos that we're developing are just a vanilla file system, and then we're using something called a solid pod. I won't go into what that is. Just to emphasize, definitely a community-based effort, well supported by ESIP in many cases. And again, my takeaways, having wrestled with this for the last 5 years, you create modular ontologies, use standard ontologies, automate the capture, because the data pipelines are far too complex for us to be doing this by human anymore. And then I argue that the semantic web technology stack is mature enough. For more info, have a look at those slides.
Yeah, we'll get these posted on our session page. And thank you, Jane. We're gonna charge ahead with our next talk, which is by Doug Schuster. Doug is a manager of the Computational and Information Systems Lab, which is part of the Data Engineering and Curation section of NCAR, the National Center for Atmospheric Research. Take it away, Doug.
Okay, thank you, and thanks for inviting us to participate in today's session. The talks have been of interest so far. And I think really what our project is related to is the topic of dealing with these large data sets that Renee mentioned, as well as sharing software. So as mentioned, I'm Doug Schuster. I'm one of the co-Is on this project, which is an Earth-Cubed research coordination network titled Determining Best Practices for Preservation and Replicability of Model Data. The other co-I is Matt Marinick, and the lead PI is Gretchen Mullendor, who's actually a modeling researcher. So she brings that insight in leading this project. So really what motivated this project? Well, I come from the data manager perspective, and we've gotten a lot of questions recently that are related to evolving community open access expectations from publishers and funders of what do I really need to preserve and share to meet these requirements when I'm producing large model outputs? Just what was used to produce a chart or graph, or all of the model output? And that question has been a challenge for many in the research community that we deal with in the atmospheric sciences. And that's really what brought this project into focus. So in terms of the motivation, what do we do about model data? For our community and for others, we think as well, we know the answer is not to preserve all of the data and output typically. Outputs in our field can be terabytes to hundreds of terabytes to even petabyte scale, which is too expensive to really preserve and share for the long run. And really not all outputs are relevant to the research topic or the finding in a peer-reviewed publication. So it's really good that researchers are able to hopefully pick what's really needed to support replication and reproducibility of their research. So our project started back in 2020, and we brought together a diverse group of modeling experts really to develop preservation guidance. So we brought a number of experts from the scientific community in atmospheric sciences and hydrology and oceanography. So it's a little bit out of the realm of what we're discussing today, but I feel that a lot of the outcomes are relevant to this community as well. So we held a couple of workshops with many from the same groups in 2020, virtual of course. We worked to develop a list of simulation descriptors to the first workshop, and then we used that to really seed the rubric and output preservation classes, which I'll get into in a couple of slides. On the second workshop, the participants refined the rubric with an extensive set of use cases. So what are their use cases? They'd run them against the rubric, see what the scores were, do they make sense? And then at the conclusion of the project, which will probably be next year, we hope to disseminate a best practices document to the broader community that will be published in a peer-reviewed journal. Currently, we have one available on the website, which is listed at the bottom of these slides if you're interested in seeing what's gone on so far. So as been discussed earlier, through the discussions that we held, there are some components of simulation research that should be preserved and really shared for all projects. And these include the simulation code, the initialization data, the setup, the pre-processing code, and the post-processing code. And that's so really others can take a look at how a simulation experiment was configured and set up and rerun that configuration or use it to inform how they might want to run a similar experiment of their own. Some of the barriers that impede sharing of this information are proprietary restrictions on code or data, access issues. You know, if you are putting data on a hard disk, it's challenging to access that data, or if you have a slow internet connection, it can be challenging to access large data volumes. And then finally, one that's come up quite a bit actually is cultural resistance in the communities we've dealt with. Researchers typically aren't rewarded for sharing code, software, data, and the citations associated with that and their merit system that are in place at universities and in the private sector. Actually, it's the reverse. They're shared for publications and citations of those publications. And in many cases, researchers like to hoard their code or data and produce as many publications as possible off of it before they share anything. So that's one of the challenges that we've run into and that has been expressed at some of our workshops and some of the open access discussions that we've seen. So we'll get into the rubric a bit more here in the next couple slides. So we had to come up with a pretty targeted purpose because there are a lot of components to simulation research. So this rubric is really designed to assist a researcher in determining what simulation output should be deposited in a Fairline community repository to communicate knowledge. So on the next few slides, I'll briefly go over what the rubric looks like. So there are a number of different descriptor themes in the rubric. They include a big picture question. And then there are descriptors that are used to inform that big picture question. And then finally, there are a number of different classes, 3 different classes associated with each descriptor. So the descriptor will be defined. The user of the rubric can choose what the exact class is that they think fits their simulation experiment best in the end. One leans more towards preserve less output and one leans more towards preserve more output. So I'll go to an example here. So one of the descriptor themes is cost. That's one we all have to deal with really. Is it more costly to rerun a full simulation workflow or preserve model output products in a Fairline repository? So the individual themes for this general area of discussion is the cost of running the simulation workflow. And then the repository data management services cost. I think in the past, it's more or less been covered to preserve your data in repositories in a lot of different communities, but now it's not necessarily the case when you're dealing with, you know, tens to hundreds of terabytes of data that becomes expensive to preserve and share over a predefined period of time. So that's really what our research community was running into and dealing with. They couldn't necessarily share the model data they were expected to share. So this is what that looks like in the rubric, in one of these sections within the rubric. So I just mentioned the headers. We have the big picture question. What's the cost to produce your simulation workflow outputs? So you have the computational cost of running the simulation workflow. If it's small computational cost, no special platform needs, you'd score class 1 on this row. If it's high computational cost, you need a specialized compute capability. Then you'd score class 3, which weighs more towards preserve more output because it's tough to rerun the simulation workflow for others. There can also be a human resource component of running this. That's the case always. Is there trivial effort required to replicate a simulation for most end users? Then we weight the score towards preserve less output. So you can kind of get the feel for how this rubric works, and then you end up with a composite score in the end based on all these different sections. So just to follow on this, we have the repository data management services cost. This kind of balances out. Is it easier to rerun the simulation, or is it cheaper to rerun the simulation or preserve data for the long term in a Fairline repository? So you have class 1 in this case, where the community repository curation expenses are prohibitive, possibly due to the large volume of the expected outputs. Or class 3, where it leans more towards preserve more output, where it's inexpensive to curate the simulation outputs that you need for a minimum number of years in that community Fairline repository. So there are 5 big picture themes that are in this rubric. One's community commitment. The question here that I'm not going to get into in too much detail is, does the project fall into data production or knowledge production category? So a data production example would be the community coordinated climate model experiments, the CMIP experiments, where you produce large volumes of data, and really the purpose is for others to use the data to produce their own research out of it. Knowledge production, briefly, is I'm running a simulation experiment that I'm going to write a paper and findings from directly, and I don't really know if others are going to reuse the data that's produced from that. So that's really what this rubric is geared towards more, is the knowledge production category. There are a number of others that are listed here that I won't go into too much detail, but you can kind of get the feel for what they'd be. Research workflow accessibility. Is it easy for others to really rerun a simulation workflow? Data accessibility. Would it be reasonable to expect others to access and use simulation workflow outputs? Research feature reproducibility. Are physical features generated by a simulation reproducible? And then finally, cost, which we just discussed a bit. So once a user works through the rubric, you come up with a total weighted score, and they go into different bins. This is how this is structured now. So if you have a lower score, the recommendation out of this rubric is to preserve few simulation workflow outputs. If you have a higher score, the recommendation is to preserve the majority of simulation workflow outputs. And then we link to reference use cases from each of these bins. So hopefully the user can look at what others have done when they get a score like this and apply that logic to their own use case and what they really do need to preserve for their simulation workflow. One thing I'll mention, the hope is that when you're designing a project and starting a project, you'd go through this process at that point. So you'd know likely what you need to preserve, and then you can plan where that will be preserved in a Fairline repository and include anything in a budget that's needed to do that. And then you can justify what you're preserving to funders and publishers by hopefully referring to what score you got on this rubric. Finally, I'll just briefly discuss some ideas that have come out of our research coordination network in addition to the rubric. This topic of replicability versus reproducibility, which the National Academy's report was produced on, is really an important consideration for modelers. We get a lot of questions, do we need bitwise reproducibility? I don't think that's really a reasonable expectation when you're looking at any of these workflows. It's more of, can you match the science findings that was produced through a simulation workflow? So that's what we're really focusing on with this rubric and what you preserve in terms of code. One other finding is that research that's primarily oriented towards knowledge production typically preserves minimal output in repositories. And then data production oriented research needs to really include appropriate resources to support anticipated data preservation and community data access needs. There's no individual technology that can solve the data needs you need, such as the cloud. It's a great resource, but you need the curation aspect and the metadata and all the different components that have already been discussed in some of the other talks today, really to support reuse of data and replicable workflows. And then this is a lot of work for researchers that aren't familiar with, all the different standards that have been discussed today in terms of metadata and provenance tracking. So there needs to be resources out there to assist researchers in data and software curation. And some communities don't really have good repositories available that they can deposit their data in. So there needs to be some more infrastructure available in terms of that for selected communities. And then finally, a large challenge that we've discussed in our workshops, and I mentioned these cultural barriers that prevent modelers and researchers really from embracing open software and data principles when they're not rewarded for embracing those principles in their own merit systems in their universities or in the private sector.
Doug, we're at time, just so you know.
I'm done right here. So for next steps, we're going to continue to engage publishers, sponsors, and professional societies. We're going to have a couple more additional workshops to refine the rubric and explore the emerging themes in 2022. And then finally, we're going to work to publish the outcomes. So if you're interested in following what's going on in this project, please email me and I can put you on a mailing list where we post updates and discuss upcoming activities. So thanks for your time.
Thanks very much, Doug. And yeah, just a reminder to everybody, please go to our collaborative document for questions and answers. We've been sharing links in the chat for that. Our next speaker is Dr. Michael Barton. He is a professor of human ecology and landscape dynamics at Arizona State University and director of the Network for Computational Modeling in Social and Ecological Sciences, or COMSISnet. Take it away, Michael.
Have to unmute there. Thanks. Thanks for inviting my colleagues and I to be able to talk to you about a somewhat different kind of non-tabular data, model code that Doug mentioned in his presentation. COMSISnet began as a pilot project back in 2006, but was actually funded in 2009. It's currently part of the NSF Big Data Hub and Spoke network. The main parts of COMSISnet, just to kind of give you an idea of what we do, it's a scientific network, large scientific network, and we have an online science gateway that provides an open access digital repository for computational model code. We also have education and training programs and a platform for knowledge exchange. I'm going to focus on the digital library, given the focus of this session. COMSISnet tries to promote best practices, standards, in order to make scientific models accessible and useful. And that's the same kind of goals that the rest of everyone else participating here has for scientific data repositories. COMSISnet, the scientific network, has over 3,000 members now worldwide. Just to get an idea about the use of the resources, in 2020, even with the pandemic, we had almost 32,000 individuals that utilized the gateway in over 56,000 sessions, representing almost every country in the world. Our computational model library is a Fairline Repository. We have almost 900 models, code bases published there. Over 100 new ones were published last year. And even last year, we saw over 38,000 downloads of model code. As we've heard today, there's increasing support and promotion of trying to make scientific data fair and curated in these Fairline repositories. But there's still pretty limited recognition about the importance of making the code fair, and especially for computational models. But computation is ubiquitous. It's widespread throughout all of science now, and computational models are especially important. I mean, Doug's discussion about Earth system models, but even beyond that, they're important for studying complex socio-ecological systems, and they're often now the primary laboratory for scientific research. Just as a sense of how this has grown, this is membership in our network and models in the library since founding. So this is for social and ecological sciences, and a sister organization, Community Surface Dynamics Modeling System in geophysical sciences, show the same kind of increase in the importance of scientific computational models. COMSIS has carried out a recent bibliometrics analysis of all papers in ISI Web of Science dealing with one kind of computational models, agent-based or individual-based models in ecology. And this shows the rapid growth of the importance of modeling in science. However, it also shows that most scientific model code is not accessible in Fairline repositories or at all. Like over 80% of the papers published do not have accessible code to work. So what do we do about it? How do we improve this situation? And at COMSISnet, we think that we need to look, include them, but move beyond the technologies of digital curation and think about fair practice, both for data and code, as a collective action problem in science. How do we manage and grow this common pool resource of scientific knowledge for the collective good. And there's two domains, intersecting domains, where collective action is needed. One is with scientific practitioners, and Doug talked about this. How do we get scientific practitioners to publish well-documented data and code in a reusable form in trusted, open access, fair repositories? At the same time, scientific repositories have to provide these persistent, trusted digital libraries, but also do their part to enable and encourage fair practice by scientists. And so kind of grouped collective action in this sense into the 4 R's. We need rules and standards, best practice guidelines, right? We need to recognize and reward scientists who make their code fair with professional advancement, reputation, resources. And then we also need requirements, kind of the stick versus in the carrot and stick, by funders and journals and professional codes of ethics to require people to do this. And I want to review quickly some of the ways that ComSysNet is trying to implement the technology and the social institutions to do this. So if you look at standards, we have standards for model developers who publish code in ComSysNet repository. There's a required minimum for metadata that they have to fill out. Title, description, operating system, language, contributor information, license, right? They also have to upload not just source code, but source code and a separate documentation file. They optionally can upload data and example results files, that kind of thing that Doug talked about. There's additional optional metadata that we encourage them to enter. It's not required. Publications and references and things like that. And then we provide kind of guidelines for best practices for documentation, data standards to try and make models more useful. And then we create a simple online wizard to make it easy for people to do these things, upload the code, documentation, and create metadata. This is what it looks like, one part of it. And you can go and look at it yourself if you'd like. On the other side, we also have standards for the repository for ComSysNet. And we upload our code in packages in a standard file structure with code in one area, data in another, docs in another with documentation. And we also use standard metadata formats using the code meta standard that are both machine and human readable and making them exposed to internet searches. This is really parallels kind of stuff Renee's talking about for EDI standards for code. We also try to provide recognition and rewards to scientists who try to make their code fair. We provide citations for all models. All ComSysNet members are required to cite models in their research. If scientists ask to have their model peer reviewed, which we enable, and they're successful at this, then we mint a DOI for it and give it a visible badge. These are kinds of things that can go in people's CVs and can actually generate citation counts to start to give them professional awards that Doug talked about. For example, we also have worked out an open code badge that can be added to publications, links back to the code. And we're going to move to be following new NISO standards for badging. And then we do download counts. Requirements, unfortunately, are still more aspirational. We're working with a number of journals to try and get them to adopt an open code badge. Some are starting to do this and try to recommend that authors make their code available in fair repositories. And we're working to try and encourage funders to also require fair code. And there's a couple of references. I know these are going to be published, so you can see these later. And then quickly, I want to mention some future plans we're trying to do. ComSysNet is working with a number of other modeling organizations to set up something called the Open Modeling Foundation. This is an initiative to try and put together an international alliance of modeling organizations to coordinate and administer standards and best practices for computational modeling. And there's been a series of planning workshops over the past few years. The ESIP has participated in these, and we hope to officially launch the OMF by the end of the year. And then it looks like we'll probably be having new NSF funding to develop cyber infrastructure that can help support reproducibility and interoperability, make this possible, as well as educational practices that can help people at least know how to use these and understand how to follow best practices. So we want to acknowledge all the folks and organizations that have supported CompSysNet and currently do so. And thank you very much. I push
Thank you, Michael.
Yeah.
So we're now going to move into the breakout session, part of this session. And what I'm going to do is I'm going to put up a screen here describing our breakout groups. Hopefully everybody can see that. And so we have 4 breakout rooms that we've created. And those breakout rooms have 4 different themes. The first is complex ecology and environmental data sets. The second is small moving platforms, drones, etc. The third is data and code from model simulations and other computational research. And the fourth is potpourri. And so each of these is designed to let people discuss what they've heard in the talks today. So we're sort of splitting up our speakers into these different breakout rooms. And then we would like our participants, our meeting participants, to join the breakout room that they're most interested in. This slide that you see here has links to the notes with some prompts for discussion in those breakout rooms. This is slide 8 in our collaborative document. So you can go ahead and go here to find those, and let me put that in the chat as well. So that's dropped into the chat. So we're going to have Patty open up breakout rooms now. Participants, please join a breakout group of your choice and assign a note taker and a reporter when you get there. You'll also need to enter the people that are in the breakout groups. Put your names into this collaborative document that you'll find. And then look at the prompts. We have probably about 10 to 12 minutes for breakout rooms. And then we'll bring you back and we'll have a report out session so that each person or each breakout group can report on one highlight from their breakout group. I think that is all.
Okay, I'm all set. If you want me to go ahead and open them up.
Okay, let's go ahead and yeah, we'll send people away. Presenters, please go to your respective rooms, and then we'll let participants choose their path from here.
Okay, we're down to 20 people who haven't joined. That number is going down.
Okay. Folks, if you're undecided on group 1, 2, and 3, and you have data that's you're interested in publishing data that doesn't fall into those categories, I would suggest potpourri. And yep. Patty, we should probably, let's see, what time is it?
I'm having trouble joining a breakout room. I clicked on the room I wanted to go to, but now it's just blank, and I can't see something.
Huh.
I'm not sure if I'm able to.
Which room did you want to go to?
I believe I clicked on room 4.
Okay, I'm going to go ahead and put you in there.
Hey, this is Kate Rose. I was also not able to join room 1 is where I'm trying to go.
Okay, let me put you in there.
Okay.
A lot of times if they're using a browser version of Zoom, or sometimes they just don't have the functionality. Could I be
Yeah, and
pleased?
I see some people putting requests to go to certain rooms in the chat, and I'm gonna follow those orders.
I got Mark.
Okay, I did
Still
Sean.
one. Yeah, I did Sean too.
Oh, okay.
So we're down to
Got about 8 people
8
unassigned.
people, yeah, not including you.
Okay.
Did we miss anybody in the chat?
Don't see anybody there.
I think I clicked on, I could see the document, but I don't think I'm in the room because I'm still hearing you guys talk.
What room would you like to be in?
The drone room 2.
2. Okay, there you go. Okay, we're down to 8 minutes left. It'll send out a message when there's a minute left, and then it'll bring everybody back after 12 minutes.
Okay, great. And that'll put us at, okay, so we'll have 7 or 8 minutes at the end to kind of wrap up.
If anybody's still on and can hear me, if you would like for me to put you into a room, I'm more than happy to do that. Wonder if those people walked away.
Yeah, could be. Those are the people that are.
There's only 6.
Took a coffee break. Yeah, that's fine.
And I will let you know that you, this session had the highest number out of all the sessions going on.
Oh.
81.
Wow, cool. That's good.
The second closest was 53. So.
Oh, wow.
Yeah, by a lot.
Right. People liked this session. That's good. I thought some of those speakers were really good. So I'm happy that people picked up on it and showed up. Patty, can you see my report back slide?
Yep.
Okay. Looks like people should be coming back. Oh, yeah.
Oh, sorry. Now it's the last minute.
Okay.
My bad.
And looks like we're about back.
The rooms will close in 5 seconds.
5 seconds. Okay.
Yep. Okay, rooms are closed.
Okay. Welcome back, everybody. So we're nearing the end of the session. We're a little bit behind schedule, as expected, I guess. So I think what we want to do now is we want to have a little bit of a report back session. So you know, it's okay if the groups didn't make it through all of the prompts. That's expected. We never have enough time for everything. And I also am expecting that there's a fair amount of overlap in what these different breakout groups we're talking about, and there's some overlap in our talks today and things. But I'd like to go around to the reporters in the 4 breakout groups and have each breakout group just tell us one takeaway message or one highlight of their discussion in the breakout group that they could share with the group. And then meanwhile, feel free to write these down in the collaborative document as well. So why don't we start with breakout group 1? Could the reporter from that group tell us a highlight?
Sure. This is Bruce. Key points: the content hashes were useful as an intermediate identifier, particularly early on. A note that Zenodo does have the ability to search based on that. And then there were 2 things that were kind of related to this, those links for targets and Wholetail or in the Slack, as some things that were just generally related to this topic area.
Okay, great. What about breakout group 2?
So there were just 2 of us
Okay.
talking about federal common need for infrastructure. I guess we highlighted particularly the real need for data product levels. It's amazing how useful those can be when you're needing to archive data and just having a standard about which data to archive. You can get so much data coming off a drone that what actually needs to be stored where, but we need product levels defined for us for that.
So you mean product levels that would be something like, raw data and derived data levels of some kind?
Yeah, exactly. And how do you version that? Same as satellite data has, but we need it defined for, and it's broader or more complex because there's so many different types of data that you can get off a drone.
Okay, great. Let's hear from group 3.
I can bring up some of the topics real quick, and others can chime in if they want to. We talked a lot about metadata standards and best practices, how it's really important to archive a snapshot of code that's used to support a research outcome in a repository such as Zenodo. GitHub is more of a collaborative development platform versus a long-term repository. And then Michael talked a lot about the work they've been doing with minting DOIs for peer-reviewed code. And then also the Open Modeling Foundation, which is working on the challenge of how do we incentivize researchers really to follow open science best practices, which is a social science question that's come up in a couple different talks. Do you have anything else to add, Michael?
No, I think that's pretty good. People brought up the issue of licenses and kind of the idea was go beyond the technology if we want to try and not just archive code, but make it fair and reproducible. That involves effort, like you said, on the part of individuals. How can repositories reduce that effort, facilitate individual scientists, and incentivize them?
Okay, thank you. And a quick report out from breakout group 4, please.
Okay, I can do this quickly. So I think what we found out is that other repositories in about the same situation that we were when we started thinking about this, and we're hoping to take this document further and get a lot of feedback from other people, other repositories, other users of data, what actually should be archived and where it should go, especially code models and the licensing issues involved in that, and things like field sheets, other documentation that go with the data, where should they go, how should they be best handled, and yes, not and, that was it.
Okay, okay, great. Well, so we are at 3 p.m. Eastern, and so I'd like to heartily thank all of our presenters. I really appreciate those great talks, and I want to thank all of our participants as well. We'll go through the notes, and we'll follow up with people, anybody who's left their contact information in our meeting notes or anything like that. We'll definitely follow up with kind of a meeting summary and further links, and I think this will be archived by ESIP as well. So we appreciate your participation, and we will be in touch.
Thank you, all the organizers. Great job.